Hello everyone, this is Module 8, Part 2. We're starting out in the textbook, page 289. So get your textbook out, get your notes out so you can take notes if you want to, if you haven't already taken notes. And have your textbook out so you can look at the pictures as I'm talking about this stuff. We're going to talk about work and power. So what is work? First of all, work is a transfer of what? Work is a transfer of energy. Okay, so if work is a transfer of energy, what are we going to measure it in? We're going to be measuring it in joules, right? So the product of a force in the direction of motion and the distance the object moves is where we get our equation work equals force times distance. This only works if the force is in the same direction as the distance the object is moved. Okay, so two things are required for work to be done. One is an object must move, and two is a force must be acting on the object in the direction of motion. Okay, so work equals force times distance. So your book talks about a man lifting a box. In the first picture I have here, he's just standing still holding the box. So he is exerting a force on the box with his hands, and that first force is going up against the force of gravity, right? Is he doing work on the box? Well, you have to have a distance, right? So if there's no movement, there's no work being done, okay? On the next example, he leans over to pick up the box. There's a force of his hands pushing up against the force of gravity, okay? And so the force of his hands is creating this movement in the same direction of the force. Is work being done? Yes, work is being done, okay? Down here, you have him moving, and he's holding the box. So you have the force of his hands holding the box up. The force is going this direction, and then he's walking. The movement's going this direction. Are his hands doing work on the box? No, because there's no work being done because the force is not in the same direction of the movement. So you have a force and you have a distance, but if they're not in the same direction, no work is being done on the box there from his hands. And then in the last example, he leans over and he scoots the box along the floor. And so he's putting a force here going in this direction, and the movement is going in the same direction. Is there work being done on the box? Yes, there's work being done on the box because you have a force, you have a distance, and it's in the same direction. For those of you who are taking notes in a composition notebook, why don't you pause the video and just go ahead and try this out, figuring out the examples and what form of energy they are. Let's practice using our equation. So example 8.3 says, you lift a book from the floor to a bookshelf 1.5 meters above the ground. You exert a 19.6 Newton force upward, lifting the book. How much work did you do? So you list your knowns, so you know that your force is 19.6 newtons, and you know your distance is 1.5 meters, and you know that your work is going to be in joules, and so you take your equation and you plug in your numbers. So work equals 19.6 newtons times 1.5 meters equals 29.4 newtons. Now, what if I tried to do this equation with 1.5 feet instead of 1.5 meters? Or what if I had the meters in a different form? It wouldn't work because I'm looking at this and I made a mistake. Just kidding. That's joules. It wouldn't work because joules is a Newton meter, and so you have to have your distance in meters to get joules. Next, we'll talk about power. So we have a really long driveway, and when it snows, Sometimes the snow is too heavy for our equipment to plow it because we just have a plow hooked up to a riding lawnmower. And so sometimes my husband and my two oldest sons have to go out and use their snow shovel to shovel the whole driveway of heavy snow. And it takes them, I would say, at least an hour. If there's ice chunks, they have to break up longer. Okay, that same amount of work can be done in like 5 minutes with when our neighbor comes over with his plow attached to like a four-wheeler thing. And so power is how much work is done per second. It's a rate of work. So power equals work divided by time in seconds. To do work faster, to do work at a faster rate requires more power. So to do work faster, you increase the power. To increase the power, you would increase the amount of work, or you would decrease the amount of time it takes to do the work. When we talk about shoveling snow versus a plow coming through, moving the snow requires work, and the plow can do the same amount of work in less time, and so that means it has more power than a person shoveling the snow. Example 8.4, you lift a book from the floor to a bookshelf 1.8 meters off the floor using a force of 16.5 newtons. You lift the book in 2 seconds. How much power in watts did you use? So you list your knowns, okay? You list those out and notice that you have your power in watts, and that's a W, but in your equation, this W represents work. Okay, so in this equation, work is equal to force times distance. So in this equation, you don't have enough places for your numbers, but just remember that work is equal to force times distance. And so then you have enough places to put all your numbers and plug them in. So I plug in my numbers and I get 14.85 watts. Now if you look here, you have a newton and a meter. A newton meter is a joule, right? And you have joules per second. Joules per second is equal to the watt. So that's how you get watts. Part B, a girl runs up a flight of stairs in 2.6 minutes. If the work she has done is equal to 320 joules, how much power did she use to climb the stairs? So you're going to write out your knowns, but when you write out your knowns, I hope you notice that your time is in minutes, and you can't have your time in minutes. In this equation, the time is always in seconds because it's joules per seconds. So you have to do a conversion, and if you've forgotten that, I'm going to just show you how. So you have 2.6 minutes. Can you see that? Yes. And you're going to turn it into a fraction, so put it over 1, and then times line. Okay, you have 60 seconds in 1 minute, so you're going to have to put your minute on the bottom so that they cancel out. So your minute goes down here, and your 60 seconds go here, and then you just multiply across, and you get 156 seconds. Okay, then you can take your knowns and plug them into here. So this would be, your work would be 320 joules divided by 156 seconds. And then you get 2.05, and joules per second is a watt. So that's how you do that. And remember, you didn't have to separate out the joules there. You didn't have to do force times distance for this one. It was just given in joules. The next section talks about work and machines, and on page 302 and 303 of your book, it has different kinds of machines. So it's got levers, it's got screws, it's got incline planes, wedges, pulleys, wheels, and axes. So just study this. Machines are useful in basically 2 ways. Machines can make work easier by magnifying the force that you apply, or by changing the direction of your force. So machines don't actually change the amount of work, but they make the work easier by changing the force or the distance. For example, a car jack. They look different, but This is one type of car jack. So if you're trying to lift this truck, the back end up of the truck, you're going to use this large distance here and apply your small force. Okay, you need a really large force to lift this truck. So if you take a small force over a large distance using a lever, it produces a large force over a short distance. And so what you're going to do is you're going to push on it, and it's going to give you a short little distance, and it's going to lock into place and lift the car or the truck just a little bit. And then you're going to push on that lever, and it's going to lift the truck up a little bit more. So it's giving you a large force, short distance, so you have to do it more, but it's allowing you to lift something that you couldn't normally lift. The hammer is another type of lever. So you have the input force, which is the force that a person exerts on a machine, and then you have the output force, which is the force that's exerted by the machine. So your input force would be where you put your hand, and the output force would be where you're trying to remove a nail. And if you notice, if you're trying to remove a nail, if you try to remove the nail holding the hammer down here, you have a really short distance here, okay? So you're not increasing your force by a whole lot. If you have a longer distance right here, you're going to have greater force pulling out the nail. So in this example, your input force is going this direction. I put it the wrong direction. It's actually over here pushing this direction, okay? And then your output force is going this direction. So it's changed the direction of your force, so that's useful. And then if you have it this way, your input force is going down, and your output force is also going down to hammer the nail. So they're both going in the same direction, but your output distance is greater. So your input distance right here is shorter than your output distance out here, and you get a greater force on the nail, which allows you to do better work. These are what you're going to use for the upcoming equations. So you have the input force, that's the force that a person exerts on the machine. Then you have the input distance, the distance that the input force is applied over. The output force is the force exerted by a machine, and the output distance is the distance that the output force is exerted, or how far the load moves. We know that work equals force times distance, so work input is equal to the input force times the input distance, or the work output is equal to the output force times the output distance. Mechanical advantage of a machine is going to be a number. It doesn't have a unit, and it's the number of times the machine increases or the number of times it decreases the input force. The actual mechanical advantage is just a ratio of the output force to the input force. You can use this equation, and let's say you have a mechanical advantage of 5. That means that the input force was reduced by a factor of 5. In other words, it means that to do the same amount of work without the machine, it requires 5 times more effort or input force. So 5 times as much effort from the person exerting that input force on the machine. The machine's 5 times better at it. It's hard to measure the actual mechanical advantage of a machine because in the real world, there's always going to be friction. There's some friction involved, even if you minimize it. So it's actually easier to measure the distance than the force. And so if you use the ideal mechanical advantage equation, you're measuring the ratio of the input distance over the output distance. Distance is just easier to measure. The ideal mechanical advantage basically represents how much the machine is able to change or lower the input force, making the work easier if no friction was there to overcome. Notice that the actual mechanical advantage is output over input, and the ideal mechanical advantage is input over output. And one way that I remember that is that the ideal mechanical advantage, it starts with an I, and so you're going to start with in because that starts with an I. One of these is always going to be greater than the other because one of them doesn't account for the friction involved. That's going to be the ideal mechanical advantage that's always going to be greater because it doesn't account for the friction. let's say we have a lever, and on page 303 it talks about the different classes of levers, the first class lever, second class lever, third class lever, and it just depends on where the fulcrum is, where it's rotating around. So we have our input force and our output force, and I'm going to put the fulcrum on there. So I put it there. If I put it in the middle, you're not going to have much mechanical advantage at all, right? And so I gave myself a longer distance for my input force, which is going to give me more force out. So let's say this is 1 foot here. And on the other side is 4 feet. Let's also say that my force in is 100 newtons and my force out is 400 newtons. What's the mechanical advantage? Okay, we're gonna go for the actual mechanical advantage because we have forces here that we can use. And so remember that the actual mechanical advantage is the force, the output force over the input force. If I put 400 newtons over 100 newtons, I have 4 over 1, which is a mechanical advantage of 4. So that means that this machine multiplied my force by 4. Example 8.5. A ramp is a simple machine known as an inclined plane. A moving company uses a ramp on its truck to help load heavy objects, and the ramp in this example is 2.7 meters long. The ramp is used to lift the boxes a distance of 0.91 meters. What is the ideal mechanical advantage of the inclined plane? So which one is going to be your input distance and which one is your output distance? So you're doing the work across the ramp right here. So this is your input distance that you're putting the force across. So this would be your output distance right here, going up and down. This problem gives me distances, so I'm going to use the ideal mechanical advantage. Do you remember if it's out or over in or in over out? So remember it starts with an I, so we're going to do the input distance first over the output distance. So that would be, the input distance would be 2.74 meters divided by 0.91 meters, which gives you 3. And I'm crossing off my units because they cancel out. So I just get a 3. There's no units. And that means that the ideal mechanical advantage of 3, it means the ramp multiplies the input force by a factor of 3. The man's effort needed to move the box is 3 times less when he uses the ramp. I want you to think about what those numbers mean. A machine with a mechanical advantage that's greater than 1 is useful for making a job easier or faster. What would a machine that has a mechanical advantage equal to 1 be useful for? This could be useful for changing the direction of the applied force. This would be an example of a lever that has a mechanical advantage equal to 1. It's changing the direction. Also, a screw has a mechanical advantage equal to 1. You can also have a machine that has a mechanical advantage that's less than 1. And why would that be useful? Well, if you take the example of the hockey stick, if you put a large input force into the stick, you get a smaller output force, but it gives you put in a small distance and it gives you a larger output distance, and all that kinetic energy from the large distance goes into the ball that you're hitting. That makes the ball travel at a greater distance and a faster speed than it would have if you just hit the ball with your hand or your foot. If you're using a composition notebook, this is part of the curriculum notebook and it's a good worksheet to do. So I would just copy this down in your notebook and fill it out, and it will help you memorize things. We can calculate the efficiency of a machine to find out how much work we're getting out of what we put in. Remember that work equals force times distance. So work input is input force times input distance, and work output is output force times output distance. So we can put them all together into an equation to figure out the efficiency of a machine by doing work output divided by work input, and then you're going to multiply it by 100 to give yourself a percentage. So if you put in 10 joules of work into a machine and the work output is 8 joules, 8 divided by 10, that's 0.8, and then you multiply that by 100, and that is going to give you 80% efficiency. This is the on your own question 8.12. What is the ideal mechanical advantage of a ramp if its length is 4 meters and its higher end is 0.5 meters above its lower end? The ideal mechanical advantage is using distance, and it starts with an I, so you're going to do input first. So the input distance is what you're putting your force across. So that's going to be 4.0 meters. And then the output distance is how far you went up in distance. So 0.5 meters on the bottom. And if you divide those, that equals 8. So the ideal mechanical advantage is 8. Now, if the ramp was a little bit smoother, what if it was a smoother surface, reducing the friction? How would the actual mechanical advantage change? Remember, the actual mechanical advantage is the output force over the input force. I put some pretend numbers in here just to show you what this would do. Okay, so if we're reducing friction, we're going to have our input force be less. We need less input force to get up the ramp. So let's say that it lessened to 2 newtons, and this is the same. The output force is still the same. We just reduced the input force because we reduced the friction. So what that did is it went from an actual mechanical advantage of 2 to an actual mechanical advantage of 5. So it's actually increasing. The actual mechanical advantage would increase if we reduce friction by coating that surface with something that makes it smoother. Thanks for hanging in there with me till the end. Hopefully this makes sense to you. Make sure you do the study questions at the end of the module. Write down your answers, work out the problems, check your answers, and that's going to be a really good way to study for when you take your test. Also, have all of the equations written out in one spot, and make sure you also write out the units for each thing that you're measuring, whether it's potential energy or work, so that you remember what units to put on your answers. Because if you put the wrong units, you're going to get the wrong answer. Okay, good luck to you. Thanks.